So in this video, we're going to start taking a look at magnetic fields. So I'm going to start by defining some terminology that I'm going to be using throughout. So those are going to be permanent magnets, magnetic materials, and magnetic fields. So a permanent magnet is a material that maintains its own magnetic field even without the influence of an external magnetic field on it. So bar magnets that you typically use would be an example of this. They have their own magnetic field. They don't need something else to make them magnetic. A magnetic material, however, is something that can be induced to become a magnet, but if it left on its own, it itself isn't a magnet. So iron is a very good example of this. We describe it as a magnetic material, but if we just left it by itself, it actually wouldn't be magnetic. So what do we mean by a magnetic field? Well, it's the region around a moving charge, and it does have to be moving, where another moving charge will experience a magnetic force. So it's the force between moving charges, essentially. So let's have a look at some magnetic fields. So the first one, we'll take a look at a bar magnet. You may well have seen these before. We draw a field that looks a little bit like this. And in terms of putting the arrows on these diagrams, the field lines, which is sometimes called fluxons or flux lines, always go from north to south. So that's how we determine the direction of the arrows. So if you actually want to look at this, we can use iron filings, which will always align themselves with a magnetic field, because iron is a magnetic material. I've put a bar magnet under a piece of card, sprinkled iron filings on it, and you can see the flux lines being shown by the iron filings. They've lined themselves up with one. Okay. So now we're going to look at the interaction of two magnetic fields and how they look different if they're attracting or repelling. So with attracting magnets, we would draw a field like this. So we end up with a very high flux density between, in this case, the north and the south pole. And you can see the arrows have been drawn on here. The flux lines go from north to south pole. So that's what the field looks like if they're attracting. If they are repelling, we end up with a region in the middle where the fields have cancelled each other out. So what's essentially happened is two field lines have been in the opposite directions and they've cancelled each other out, leaving a gap or a region of low flux density. And that's what we get when we have two like poles pointing. It could be south or north. We still end up with this gap in the middle. So again, if we take a look at this with iron filings, you can actually see these effects coming out. So you can see with the attracting magnets, we end up with a region in the middle with very high flux density, whereas with the repelling ones, we've got a region with almost none at all, because these magnets are identical. Okay, so let's talk about the process of magnetization, and what that means is turning something which is not magnetic into something that is. So when we do this, we talk about dipoles. So a dipole is a closed magnetic field. So in the previous diagrams, we had some field lines going from one magnetic material to another, whereas in this one, a dipole is a closed magnetic field. So the field lines go from the north pole of this object to the south pole of that object, like you can see here. And then we go up a scale and we start talking about domains, and that's just a collection of dipoles that all move together. So when you have dipoles close together, they will usually align themselves with each other, and that's what we call a domain. So in an unmagnetized material, the domains will have random orientations. They'll be pointing in all sorts of different directions, and that means all of their fields, when they superpose together, their magnetic effects cancel each other out. So if something that's unmagnetized, all of the little fields and the domains cancel each other out. Whereas when we magnetize a material, what we're doing is we're lining up all of the domains so that when they superpose with one another, and superpose is just a fancy way of saying essentially we're adding them all together. What that does is, because they're all lined up, they create a stronger magnetic field. So let's take a look at that in a diagram form. So on the left, you've got an unmagnetized material, because what these arrows indicate is the orientation of the domains. When we magnetize it, we line up all of those domains there. You'll notice that they don't all necessarily have to go in the same direction. So they line themselves up with an external magnetic field, but they don't all have to go in the same direction. They'll just all be parallel to one another. Okay, so that's an unmagnetized material. A saturated magnet would be one in which all the domains are aligned. So we can see on the right-hand side, we would describe that as being saturated or almost saturated realistically. We would actually want the three down arrows you can see to be pointing in an upwards direction, but that's very close to being a saturated magnetic field, or as strong as it can be. Okay, so how do we actually magnetize something? Well, most people have seen this one. You use a permanent magnet to turn an unmagnetized material into a magnetized one, and you do it by stroking it with the magnet. So what we're doing here is we're aligning all the domains, and we're doing it by applying an external permanent magnet. And we use a stroking motion, so you can see the path that we'd use shown on the diagram. The other way we can do it is by applying an electromagnet, or which is what we've got here. So what we do is we wrap the thing we want to turn into a magnet with coils of wire, and we run a DC or direct current through that wire, and that means the current has the same value and it's always going in the same direction. And if we do that, we will turn the iron nail into a magnet for as long as the current is running through it. So this is an iron nail. So iron will only be magnetic when there's another field making it magnetic. So in this case, this electromagnet is forcing the nail to become a magnet, and it will stay that way as long as the current is applied. So in terms of what that would look like with iron filings, it looks a bit like this. So essentially, the current carrying wire is turning the iron nail into what's effectively like a bar magnet while there is a current. Okay, so that's the two real ways we magnetize something, using a permanent magnet or using an electromagnet. But if we want to make this process a bit faster, there are two things we can do. One thing we can do is we can heat the material while the fields are being applied. So normally speaking, just heating a material will demagnetize it, because it makes them all of the different dipoles and domains go in random directions. But if we heat it while we apply an external magnetic field, that actually allows the existing dipoles to break out of their domains, and then they line themselves up with the external magnetic field. So heating is a way of breaking them out of their existing orientation. The other thing we can do is hammering material, and that is exactly as it sounds like. You are literally hitting things with a hammer, and that again breaks the dipoles out of their existing domains. And again, if you apply an external magnetic field, they will form new domains all lined up in the same direction. And quite often these two processes are done together to really speed up the process. So you'd heat it and then hammer it. That would be our process, especially if we want to create permanent magnets, which is a more difficult process. Okay, so what makes some things easier to magnetize than other? Well, first of all, we just categorize those two as being soft or hard magnetic materials. So a magnetic material that is hard requires a large amount of energy to magnetize, but that also means it requires a large amount of energy to demagnetize. And that's why we use them for permanent magnets. Is once we've magnetized them, they will maintain their magnetic field for a very long period of time. But to produce a permanent magnet, we would want to be heating and hammering with our external field, because it's a very difficult process to do. But once you've done that, that will stay that way for a long time. And steel is a classic example of a hard magnetic material. So a lot of permanent magnets are made out of it. A soft magnetic material only requires a small amount of energy to magnetize, so it's easily turned into a magnet, but it also only requires a small amount of energy to demagnetize, so it will very quickly stop being a magnet once you remove the external conditions. So these are great for electromagnets. So the iron nail, for example, that you saw earlier, the iron is a soft magnetic material, so it will line itself up, or the domains will line themselves up with a field from the coil, and that will produce a strong electromagnet. And iron is a classic example of a soft magnetic material. You'll see it used time and time again with electromagnets. And that concludes this video looking at magnetic fields.